Am I live? OK. Hi. So I hope everybody has the time to settle down. Good. It's getting a little quieter. So I'd like to welcome you all here. It's a big crowd. I'm really happy to see all of you here. I hoped Kubernetes would spark the interest. It certainly has been a pretty exciting technology for us over the past 2 years. Today I'm going to be talking about Kubernetes in a specific way, and that's running all of your Kubernetes workloads on AWS EC2 Spot instances. I think the reason why we started playing with Spot instances was naturally the costs and the savings which we could realize actually on our EC2 part of the AWS bill. But the twist I want to make to the presentation, and which I want to spend a little bit of time today, is that during that, we learned a lot about the resiliency of our apps. And that is actually going to be, I think, the biggest takeaway to this, that adapting to to the behavior of Spot instances can actually make your apps a lot better, a lot more resilient. So let me maybe just kind of stop very, very quickly over where I come from. I come from Delivery Hero. I manage the logistics engineering team, and we manage our own delivery feeds. So we're a food delivery company. So you know us as Lieferheld, as Foodora, as Pizza.de in Germany. But we also operate in 40 countries all over the world, many continents. And about 20% of our business we employ, or we have riders as freelance partners, which deliver the food for us. So it's not the restaurant. And in Berlin, we have an engineering team which writes all the code supporting that. Where as far as AWS goes, we have workloads across 4 continents: North America, South America, Europe, Asia, actually also up until recently Australia. And just to give you an idea of, let's say, the scale we're talking about, to bring this a little bit closer to you, our workloads for purely logistics is around a few hundred Kubernetes nodes running simultaneously. Of course, it can go up and down quite a lot, depending if we have some batch workloads. But this is, let's say, the scale at which we made this, the contents of this presentation work. So to give a little bit more practical and to kind of just bring logistics tech from Delivery Hero a bit closer, nothing extremely surprising. We have Rails and Spring for web workloads doing their job very well. No need for us to experiment with something more exotic. We do, however, have Scala and Akka, which are doing a really good job for our real-time apps, especially our dispatching algorithm. And also, in the past year or two, we've really become data-driven. And we use a lot of Python. We use a lot of R for more batch tasks. And also a lot of solvers for some of our optimization problems. Persistence-wise, we use mostly Amazon RDS with Postgres, and more recently, we're switching a lot of use cases to DynamoDB, when we realized a lot of our usage just doesn't fit the RDBMSs anymore, and we just realized how much more DynamoDB is scalable. And as far as Kubernetes goes, right now we actually don't use Amazon EKS yet, but our system engineers, they're actually sitting somewhere around here, I think they actually this week transitioned our QA environment to EKS. Currently, we use kops, but for the purposes of this presentation, it will work no matter what way of provisioning Kubernetes you use. So if you are from Germany, you might know Foodora. So Foodora riders is what we, and they're supporting them is what we spend most of our time with. This is me delivering food somewhere near Rosenthalerplatz. I think this was almost a year ago. And so what do we do? Essentially, we manage the whole end-to-end experience for the rider. It starts with hiring them. A huge part of our business is actually staffing the right amount of riders. So it's not, everybody thinks it's just finding the best route and assigning the best orders. But a lot of optimizations we do actually are about staffing the riders as well. We developed the mobile app, the tracking of the riders to see where they are and being able to assign them the best orders or make them be able to choose the best orders that they can deliver. And of course, following up to payroll, to actually kind of going full circle with the whole employment or freelance experience. So this, I picked up that microphone picked me up. So this is a little bit how our day looks like in terms of load. So this is a typical day of a logistics, and not just logistics, but a delivery hero engineer, right? So it starts at midnight, and around 4 or 5 p.m., Asia lunch picks up. So there you have the first peak. Then around noon our time, Asia dinner suddenly coincides with Europeans going to lunch and ordering food. And then you can see the rest. Why I'm actually trying to show this, and what I'm actually trying to show this on a graph is that cloud and elasticity has been always kind of like a really basic thing for us. We've actually never really thought of operating on pre-provisioned hardware, and we've always been using auto-scaling, because when you have these usage patterns, it's just really so hard to expect peaks. So for the purposes of this presentation, again, I think I'll assume most of you know what an auto-scaling group is. So who uses auto-scaling actually in the crowd? Who kind of goes to the EC2 console and clicks the blue button, launch new instance, and that's most of his workload? A few, that's OK. I'd recommend actually converting that to an auto-scaling group with the size 1, like the moment you come home. And then if I pull out like a single country, you can see the traffic influx can actually be pretty rapid. So I think this is actually my home country. This is Czechia. So you can see at 11:30, everybody logs their computers and goes to lunch, or better for our case, orders food online. So at 11:30, suddenly we have these influxes of traffic. So going to what I was telling in the beginning, why did we start playing with spot instances in the first place? And that was to save money. It is, I think, well, I'm pretty sure it is the biggest component of our IT spend, of course. And that was our primary goal. If you look at a typical delivery hero AWS account bill, it looks oversimplified, a little bit like this. This EC2 typically is always more than 50% of our spend, and it's always the strongest contributor to our cost. RDS usually follows. In some accounts, RDS actually attacks first place. And this graph already takes into account that you just did not do this naive migration to Amazon, but you have also already started to using a lot of the application services, the managed services that are metered by usage, not just by an idle instance running time. So imagine DynamoDB, SQS, which is just paid per message, or by how often you poll, AWS Lambda, which is really just measured by the amount of RAM and CPU time you consume. But still, EC2 very consistently pops up as the biggest contributor towards our AWS bill. And again, that's why we want to focus on this here, because pretty much all of our EC2 usage is on Kubernetes nodes. We've made an all-in choice that Kubernetes is going to power our web workloads, our worker workloads, our batch workloads, our model training workloads, everything that we have in the bag. So any improvement we make on this front pretty much applies to every application we have, every use case we have. And we just need to basically make this effort once. It's not as easy as it sounds, but in practice, it actually ended up being very close to this. One common question is, why not use reserved instances, which was usually the traditional way of saving money on EC2, where essentially you go to Amazon and you commit for 1, 2, or 3 years to use an EC2 instance. And no matter if you use it or not, you're going to be paying it. It has become a lot more flexible in the recent months. They have become much more convertible, and you can basically change instance sizes. But at the same time, you still have that commitment. For us, one of the reasons why I was showing that load graph at the beginning was to show basically the daily change in load. And we could only, let's say, what are we supposed to do? We can either reserve the base load, or we can reserve the over-provisioned peak load we expect. We could also deploy a hybrid, just reserve the base load and doing on-demand, or doing reserved and then combine it with spots. But then exactly that's why we just say, OK, let's just go with spots all the way. The business itself, so Delivery Hero, still has a lot of startup DNA in it. and the business is too volatile. So for example, you might have read in the news in December, we have sold Foodora and Lieferheld and Pizza.de. It's still subject to approval, but there's a very good chance it's going to be going through. And suddenly that means all of your German traffic will be out one day to another. And what do you do with all that reserved capacity in Europe? We're not opening any new countries there. And also, I think, most interestingly, the workloads and the way we use cloud changes over time. It's very apparent in machine learning, for example, where some of the model training is suddenly 1 month very CPU heavy, 1 month it's very memory heavy, and 1 month we're going to need actually GPUs to train our models. And again, trying to figure out which types of capacity we want to reserve somehow then locks us into having that capacity and then just trying to find the ways to use it, rather than trying to think about the problems we have and then just buying the capacity for cheap to run what we need. An interesting small use case, though, we use it for Kubernetes masters currently. So we're not on EKS yet. So that's a really nice use case for us. It's running 24/7 and at a very constant load. So we do use reserved instances for our Kubernetes masters, which is going to go away the moment we manage to migrate to EKS, which I hope is going to be any week now. Actually, very, very nice experience, I think, for us. Right now, after the last batch of changes, we're pretty confident to go with it. And we already have production applications on EKS in Delivery Hero. Money, right? So how does our actual AWS bill look like? I think a lot of people find this the most interesting thing and are always most curious, right? So if you see the laser pointer, the time when we started talking about spot instances was around here. Second half of 2017, and we realized our AWS cost goes up linearly with our order volume. And we kind of figured out if it goes up and up and up, it's just going to become a hot topic, taking our time. And so we did invest that time and tried to figure out what is the best ways to tackle this. And you can see even after the first waves here of optimization, where it quickly goes down, that was spot instances for us. And it also bought us a good quarter of a year's time to basically implement some other measures. And then the really nice thing over time is it has also managed to keep our AWS bill pretty constant, because even with spots, we can be over-provisioned, and we're just growing into that capacity over time. The nice thing, of course, is then that the cost per order is getting lower and lower, which in business terms means it's becoming less of a topic with management in budgeting and with finance. So this is, of course, like a nice thing, giving you energy and time to spend on other places. This is a screenshot of a recent addition to the EC2 Spot console. So what you can see is actually a real example of savings. So this is a snapshot, let's say, from our US East 1 cluster, and it takes your currently running spot instances. So I see I have 77 instances running. You see spread over a bunch of different machine types, and it tells you the savings. And I think the 70% saving is consistently what I see across the whole world, and it really applies. So a fleet I would have paid for, or the whole lifetime of that fleet, I would have paid $1,800. I paid a little bit under $500, so which is 72% savings. And I mean, that's huge. Reserved instances will give you 20, 30%. And here you can suddenly jump into completely different territories in terms of savings. It also applies, for example, when you have very, very intense workloads. You want to basically pre-process all your historical data, and you want to spin up a huge, massive fleet of data processing machines. Again, spots will give you that same rate. Overall, if I don't have it in the presentation, but if for us that, for example, meant on a monthly AWS bill for the department goes around from 50 to 60,000 euros a month, will go down to around 20, which is for us, again, really, really huge, because it buys you a lot of time to optimize elsewhere. Who uses spot instances? Good. I actually have a thing or two to share. So just to have a quick refresher and have everybody be on let everybody be on the same page, I just want to explain very, very briefly how spot instances work. So if you go to Amazon and you launch an instance by default, it's called too much text. I'll say it first. It's called on-demand, and essentially you just rent per second nowadays, I think, and a virtual machine on which you can run things. Amazon will not take that machine away. It's going to run for you, and unless the underlying hardware fails, that's also the reason why you should always run a single instance as in an auto-scaling group of size 1. It'll stay there for you. Whereas with spot fleets, what you do is you bid on the unused capacity. I mean, at least that's how Amazon explains it to you, and the free capacity in the data center. There's one big catch to that. They give you those instances, their free capacity that they would not use otherwise, more than 50% cheaper. You just saw it's usually around 70%. But the catch is they can take away that instance with a 2-minute warning. So they're going to say, hey, I have an on-demand customer, or I have a reserved instance customer who's going to need that instance, and you're just paying for free usage, right? So for our free capacity. So you give it back to us. And the second catch, of course, is you're bidding on free capacity. There might not be any. Basically, the market can be completely saturated, and everybody, the C5 2x large is sold out in this availability zone in Frankfurt. So this is essentially the only problem, and I want to spend a little bit of time what that actually means for applications in production. A spot instance market is defined by an availability zone and an instance type. So you always bid within an availability zone for a specific instance type. So C4 2x large in EU West 1A is a separate market, and that could be sold out. So what you want to do is you want to actually diversify and bid in many markets at the same time. So you say, OK, I can use a 2x large, 4x large, different instance families, and I want to use the A availability zone, the B availability zone, the C availability zone. And that suddenly, for example, generates 24 bidding markets. So it's actually the sold out problem is actually not so big. Amazon also, in my opinion, this is my still old school with RSS. This is my reader. And if you look at the new, a lot of the work, if you look at the work going into spot instances, it's very much active. And we could see a lot of things that make using them a lot easier compared to, for example, 18 months ago. There's offerings now which are able to give you hybrid fleets, part on-demand, part reserve, part spot. You can specify everything in a visual console. If you're not super used to infrastructure as code, but that's, of course, also possible. So today, if you provision spot fleets, the console experience is very good. It's actually been, it's very comfortable. But of course, I'll always be the advocate for using infrastructure as code, and the support there is good as well. You can use AWS CloudFormation. You can use Terraform very well. Some of the resource types are a little confusing. There's a product called Spot Fleet. There's a product called EC2 Fleet. But after a few pages of documentations, it's not very hard to wrap your head around. So what I want to move on to is, what does that 2-minute warning actually mean for your applications? And what do you actually need to take care of? So a timer starts. 2 minutes countdown. And what you need to do is close all connections to the application, right? So any clients connected, any keep alive connections you have to do, you need to gracefully disconnect them. Maybe your application is doing long polling on the other hand. You need to close those connections as well. You need to stop in progress worker jobs, your sidekick, your queues, your celery, and stuff like that. You need to actually cleanly terminate your pods, your Docker containers in Kubernetes. You need to deregister the pods from the service, from the load balancer within Kubernetes, so no traffic is routed to that. And very importantly, you need to rescale to the previous capacity. Since there will be pods running on the instance that is being taken away, you need to place them somewhere else in Kubernetes. Kubernetes will do that for you, but that's what I want to talk about a little bit more to understand what components are good to make that work reliably. Maybe just to stop for a few seconds, how do you actually know that instance will go away? There is a special metadata API for Amazon. This is exactly the same place where you get your temporary IAM credentials from. And there's an endpoint which you simply pull every 1 or 2 seconds. I think 2 seconds, AWS recommends. And it returns a simple JSON response. And it will tell you scheduled for termination, not scheduled for termination. If yes, what is the deadline? So That's the way Amazon will let you know. Recently, a few weeks or months ago, they also added an SNS event, as far as I know. But this is the way we go, and I'll stop by that in just a second. So something I hear very often is like, hey, that's like Chaos Monkey. It's going to terminate random instances all over the time, right? I mean, Chaos Monkey, I should have that installed or being able to handle that anyway. Yes, but those terminations will happen not just in business hours, like people usually run Chaos Monkey. They also can kill several instances at the same time, which means if that's a significant part of the capacity of your cluster, you can run into problems. And one of the biggest things I think I was fighting was my own insecurity in like knowing that this is going to be a reliable solution for the company, but also with management, with my CTO. And that's exactly what I kind of want to demystify in the rest of the presentation and explain, hey, we're able to handle a lot of these things. And while we're doing that, we can actually make our apps a lot more resilient. So if we break it down a little bit, applications not terminating gracefully. You can have this connection reset by peer, you might know from when you browse. You can have stuck jobs which never properly report a success or error status. You can have too much of the target capacity being taken out at the same time. So if I have a service which has a pod autoscaler and is running at 4 instances, 3 of them will be taken out because they were on the same node. That service is probably going to be under capacity, and you're going to see request queuing. Or you might be running your cluster very tightly in terms of scaling, and there's just not going to be enough room in the rest of the cluster to reschedule your pods. I wanted to actually stop by in a little practical case study, and it's one of the things that we had to learn while doing this. One of the most misbehaving or the worst behaving apps on boot were our Java apps written in Spring Boot. And what you can see on this profile or graph at the top, Spring Boot pretty much consumes all the CPU it can get its hand on. So you can see we had it throttled at about 40% or so for until all the classes are loaded. And then it basically kind of chills out at about 1%. And so we never actually tackled this problem before, and we had to understand why. In this case, it was actually a combination of an APM instrumentation tool, so something like New Relic, where basically it instruments bytecode and hooks into the bytecode, and it takes a lot of time. And we also learned a little bit about JIT and Java, how it works. And essentially, you can trade off a little bit of performance over the lifetime of the app, getting a faster boot time by actually disabling some higher levels of JITting. The bigger problem, we would normally not care that the application starts so slow, but the problem was in case spot instances took out too many instances at the same time, when several of these Spring Boot applications started fighting for CPU, it actually made the node too busy and started affecting other apps. So by rolling out spot instances, we suddenly learned about this usage, which would bite us in the long term anyway, and we found good ways to fix it. So now to actually the most interesting part of it, and that's actually how do you handle spot instances in Kubernetes itself. So there's like a basic toolkit which you should always take with yourself, and I'm going to go component by component. The first one is called a spot termination notice handler. And if you remember the metadata API, which I was telling you about, that's all this does. I think it's a Ruby script or a Python script, which essentially just every 2 minutes, every 2 seconds, pulls that metadata API. And in case it finds out that node is getting terminated, it will drain it. Maybe let me just do a little check on how much I should explain this. Who knows what a daemon set is? Who knows what draining a node is? Pretty much same crowd. So just to make sure that I'm not leaving anybody behind, a daemon set is a Kubernetes, a container in Kubernetes, a pod which will run on every node in the machine. So for example, a log collector, very often it is, or something that is, you have a server monitoring tool and you want to collect metrics on every server. So this is something that runs on every machine. And draining a node means that for Kubernetes, what Kubernetes does for you, essentially, and the core of it is basically you tell Kubernetes, please launch a Docker container in this cluster of machines. And it has a component called a scheduler, which will decide, oh, this is the best machine to run it on based on some metrics. And so what it does, it taints the node, which marks, hey, don't schedule any pods here. This node is going away. It's not healthy. There's no, don't please schedule any new Docker containers here, and starts immediately rescheduling those pods on another node within the same cluster. It's going to do it gracefully. So if that, it's basically going to issue a nice termination signal to the Docker container. And if your application can handle this, it's going to close all connections properly, close all workers, and die. I think this is something that no matter if you run spots or not, you should be doing. But spots, again, made us focus on this a little bit more. Because if you have your standard on-demand instances, you will not experience them going up and down so much. So you don't focus on this, and you will just ignore those 500 errors, which sometimes pop up from time to time in your logs when a Docker container is dying. But it really made us spend a little bit of time on examining the behavior of all our applications when they are getting sent graceful termination signals. It also gives you an optional Slack notification, which has become our go-to debugging tool in the very beginning. It looks a little bit like this. We have a Slack channel, and it tells us, OK, in Asia Pacific, we have an instance terminating at 8:40, actually 2. And this also kind of made us demystified spots a little bit. So we didn't know if it's like, you get it always for 12 minutes, you always, and you kind of only have them for a few minutes at the same time. How many will disappear at the same time? All these little questions to see. I don't have a definitive answer. It does look a lot like this. So a lot of random terminations over the whole day. But from time to time, I would say we can see, for example, up to 5 machines leaving the cluster at the same time. But I think that's a more extreme case, which doesn't happen so often. But today, we are perfectly able to handle that. Again, our current usual sizes in one Kubernetes clusters will be around 50 to 150 nodes. So you see at the bottom somebody from the data science team actually using that channel to debug, noticing that four instances were terminated, and he had 25 tasks running on Airflow at the same time, which got stopped, interrupted in the middle. Airflow is a framework for running batch tasks. Imagine Jenkins, if you're not familiar with Airflow, which just allows you to run periodically tasks. And for example, that means machine learning models for us, machine learning model training for us. And so, for example, that batch use case is actually one of the things we do have on demand right now. And we're still, that's kind of, let's say, the last thing we still have on demand, which we would like to figure out how to use spots for correctly. Second component. First was termination notice handler. The second component which we have is the Descheduler. So on the screenshot, you see an interesting thing. We keep talking how spot instances can disappear, that they're going to go away within 2 minutes. But they can also stick around for a remarkably long time. So you can see this is one of the production clusters in the US regions. And you see we commissioned it 250 days ago. 2 weeks later, a node scaled up based on usage. And it still hasn't gone away. It's been there almost a year. So spot instances don't have to be necessarily ephemeral. And what the problem with this is, Kubernetes will only look at your Docker containers and where to schedule them on creation time. So what happens is, over time, that node will typically accumulate pods, especially, for example, if you have some applications which you don't deploy that often, you don't upgrade. And they will become full to the full capacity that you can reserve on those nodes. And that is a problem for one reason, and that's basically when that node will go away, there's going to be a lot of Docker containers to reschedule on other nodes. And going back to that Java example, for example, that can cause a lot of CPU stress on that node because some applications need a little bit more CPU when they're booting up. So this is a good component to have no matter if you use spot instances or you don't. It simply prevents a few things. It prevents pods of the same deployment. So imagine I have a service serving my customer data in Kubernetes. A deployment is basically a collection of horizontally scaled pods, of horizontally scaled containers. So it prevents making sure that the scaled copies of that container run on the same node. It will also try to reduce the overall reserved or actually used CPU or memory usage on the nodes and make sure that they're more evenly spread out, which is a good thing in any case. The additional bonus to this being is, of course, then if one of those nodes go down, there's a lot more room spread across the cluster to launch those new pods. So there's a bigger chance the pods will be starting spread out across the cluster, not just on one node, which happens to be very free, like can't show, like over here. Third, so that was the second component. First, termination notice handler. Second, Descheduler. Third being the auto-scaling strategy. So again, that's why I was in the beginning showing our load graph with all those lunch and dinner peaks across the whole world. We always need to have enough capacity to launch new pods. You have 4 machines going away. You need to have enough room for pods which used to run on those 4 machines in other places on the cluster. In Delivery Hero, we use 2 strategies that I know of. Probably we might use more. I know the first one, which my team uses a little bit better, but I think the second one is also very nice, and it's a pretty nice idea from another team in Delivery Hero. So the key point for us is we do not scale by CPU usage. It is generally discouraged in Kubernetes to do that in general, but the way for us was to actually collect how much. Again, maybe let's do one question. Do you know the difference between requests and limits on pods in Kubernetes? Who does? OK. I'll still maybe do a little refresher. On a Docker container level in Kubernetes, you are able to specify 2 values. One is called requests, which is how much CPU or RAM that pod will always have reserved. It will always have half a core equivalent, and it will always have 600 megabytes of memory. Limits is how much it can like go above that reservation and burst. So if you reserve very little and let the limits go very high, your applications will be just fighting for resources. You can also set limits the same as reserved, and you will always have dedicated resources for your pods across the cluster. So that is the key thing for us, that we scale the spot fleet based on CPU and or RAM reservations. Depends on the usage type we have. So imagine we have a fleet of CPU-bound machines. We say we always want to have that machine at a 70% level reservation. So that 30% is left for bursting, but we always are able to place that. It's more important with memory, because if the pod does not have enough memory, it will simply terminate with an out-of-memory error. I'll stop by at the first strategy in just a second a little bit more. Another nice way to do this is over-provisioning. Essentially, you put placeholder pods in your cluster which do nothing. It's just like, they just sit there. But they take all those resources, but they have a low priority, which means if Kubernetes has to decide, hey, I have another container which wants to start, but there's no free room, this one has such a low priority, it will actually terminate it to make room for those new ones. So that's also like a nice way to keep like kind of an additional free buffer on top of your cluster capacity at all times. So in general, it looks a little bit like this. We have a custom-written daemon set. The secret is actually we use that termination notice handler. We patched it a little bit, and at the same time, it checks for that termination notice. It also reports metrics to AWS CloudWatch. It reports the number of CPU reserved and the percentage of RAM reserved on the node. And directly in AWS, you can specify that you want to scale a spot fleet based on custom CloudWatch metrics. In our case, we will launch 2 new machines when more than 80% of the cluster CPU is reserved, and we will terminate 1 machine when the used CPU is under 50%. This is exactly a screenshot from the AWS console. Doesn't make me too proud because you can see it's still manual. So this is one thing we're just right now rewriting with EKS into Terraform. So that is essentially for us. It's always super important for us to be sure that we have enough capacity to launch new pods in the whole cluster. One little thing, I was talking about Java. I'll still stay with JVM. One of the interesting exercises when looking deeply into our applications, how they behave on termination, was our Akka applications. So Akka is a JVM-based framework for building real-time apps. It's based on an actor model. And it doesn't really matter if you know it or not. But the big difference compared to your typical web application is it's stateful. It holds data in memory between requests. It's synced by messages between the actors. It knows how to basically rebuild that state in case the pod goes down. And it can also run in a cluster. So it's not like your HTTP request in, response out, I forgot what I was doing 2 seconds ago. It actually keeps all that state in memory. So you can imagine a pod termination affects that a lot because you need to make sure that all the data which was in memory before the termination is reinstantiated somewhere else properly. And we learned a lot about the cluster formation. So it has a non-trivial cluster formation mechanism. It needs to keep a quorum. There's several strategies. You can run into split brain situations. And I think one of the really proud moments for me in the last year was when an availability zone in US East 1 had connectivity problems. And that's always something that we were always, yeah, we can never do anything about this. It's just an infrastructure issue, and we'll blame it on AWS. But we actually found that the optimizations we did to be able to cope with those spot instances being terminated all the time. We had to implement a split brain resolver, which sees if the cluster has enough members to form a quorum, to form a majority. And suddenly, when we were looking at our logs, debugging what exactly happened during that networking outage, we've seen that the application by itself has migrated to the healthy availability zone, ignoring all the machines in that unhealthy one. And that was a really nice thing for us that, OK, hey, availability zones make sense. We can actually use them. And it's not just, it's probably better to run in one availability zone since we don't want to pay for the inter-AZ traffic. So this is like another case where this has become a really nice exercise for us to learn how our apps behave under these situations. I think what I want to recommend if you want to try this, there's no need to basically do everything at once, and you can take it step by step. Kubernetes allows you to do multiple instance groups, so you can have a set of spot instances, some on-demand instances, reserved instances. You can have more memory-based machines. You can have more CPU-based machines. And then on a pod level, you can actually specify which of those instances you want to run those apps on. So what do you do first? You take your most simple REST API with no persistence, the one that boots up in 2 seconds, has no persistence layer, has no state in memory, and move it to spot instances. See how you go. See how your monitoring noise goes up. And then you take your applications which have persistence. And then you maybe end up, like in our case with Akka, with the applications which actually have state based in memory. I think the 80% goal, if I look at our February usage down below here, in dark blue, spot instances. In red, you see the Airflow tasks I was talking about on-demand, and the reserved instances for Kubernetes masters and maybe a little other use case. So you can see there's a bit more on reserved instances. That took us 6 months. It was not from one day to another. We, of course, uncovered problems going forward with it, spent a little bit of time fixing them. But it really opened our eyes in a lot of things. So you can see right now we're running. If I sum up the whole data for February, which I had, I know, up until a week ago, you can see it's just about under 80% running on spot instances. And if I again take that, if I combine that with the 70% savings, which on average we're always achieving with spot instances, this is a huge thing for us. So I can only say that our experience with this was eye-opening. It was also a really big cost saver, reducing a lot of energy on that. And looking at the time, I think I'll be available rather for questions right over at the side. And that's it from me. So very much thanks you for being here, and thank you. I do have one actually last message, one request. We do have a booth in the startup section right over there at the end. So I was asked to send you over, and I think from what I stopped by, it's really worth taking a bit of time to stop there. Thank you again.